Last week, we released a video describing a new load development technique. That is, using Doppler radar for intermediate ballistic analysis of each shot track that you shoot when you're working up that load. Now, I actually made that video a couple of months ago, and since that time until now, I've actually put that same technique to use once again. What I did is I used that technique to work up a load for my son's HKMR 762, 308 Winchester, well, 7.62 by 51, shooting the 175 grain Sierra Match King bullet. And boy, did it work again. In fact, that analysis showed me a very interesting situation, that one particular powder charge showed me a very nice, well-behaved bullet that also happened to be an optimal charge weight node and a harmonic node. By the time I finished that load workup, he shot from the prone position 100 yards, a 0.7 MOA group at a 10-shot group at that 100 yards. So once again, that same technique really did work. I've also been using that technique to analyze the flyers that sometimes happen. Well, you know, it has happened to all of us. Bam! I shot that. Oh man, I thought I was right on. The sight picture looked good. I don't think I jerked the trigger, blah, blah, blah. Whatever it is, everything looked good. But that one round just went high or to the left or to the right. Those sorts of things. And sometimes it just shows us, well, something happened. But the analysis doesn't tell me this or that or the next thing. But sometimes we do see a poorly behaved bullet in contrast to the others, and well, there was something going on with that bullet, and so that would then give you the ability, let's say, the satisfaction of knowing I didn't pull it, that was truly a flyer. Now, doing the analysis I described in the previous episode, even with the Excel worksheet that I provided for folks to download, even with that, it's still a lot of work. I realize that. In fact, a given shot track takes, 5, 10, maybe a little bit more than that minutes to go all the way through. You really got to focus on what you're doing. You got to be very systematic so you don't duplicate or miss one, or wow, lots of stuff going on. And then I talked via email to some of the specialists at Labradar and shared with them some of the stuff I was doing. And they gave me some additional ideas, what's called data reduction analysis. Let me explain that for just a couple of minutes. Data reduction is necessary or can be very, very helpful when you have a tremendous amount of data almost replicated, and sometimes statistically a person could argue it's pseudo-replicated data. And we see that with these Labradar tracks. We can have a record at 14.5 yards from the muzzle, 14.6, 14.7, 14.75. Wow! Tremendous amounts of data. So a data reduction technique, it can be done in several different ways, but what you're doing is saying, give me one value for 14 yards, another one at 15 yards, another one at 16 yards, or you could do it in time, and so on and so forth, right? So that meant even more work, and that's a lot of tedious, monotonous. Let's take a look at this track, and now the next one, compared to the previous one. Wow, just tremendous. So I decided to work smarter, not harder. I used to program a lot years ago. So what I did is I brushed up on my current programming skills, and I wrote a program. And what it does is it does everything we want it to do, everything I showed you previously that Excel spreadsheet does, plus the data reduction techniques, plus some summarizing reports, and it does it all in a matter of seconds, just almost as fast as you can click. And then we're ready for graphing the data, and it's so easy. I got it set up so nicely. Graph that data in something like Microsoft Excel. So let me show you this software and how it works. Then we'll come right back at the end of all this and wrap things up. Okay, well, we're on my computer right now, and we're looking at a Labradar record. This is recording number SR0454, happens to be shot with that MR762 rifle and the 175 grain Sierra Match King bullets. This, if you're accustomed to looking at a Labradar record folder, this is what they always look like. That we have a report file here generated by the Labradar, and we need to make note of this: the velocity of each of these individual bullets. So shot number 1 had a velocity of 2,165 feet per second. We'll go ahead and explore that one. And the other one that we're going to take a look at is shot number 4, right over here, with a muzzle velocity of 2,216 feet per second. So now I'm going to minimize this file. And now we're going to jump into this software that I've been talking about, and the one that I wrote. And it's a fairly simple interface to use. I've got this set up so that we fill things in from top to bottom, more or less in that order. These buttons right down here are currently disabled looking. That's because we haven't completed the top part right here. So we're going to go ahead and select the file that we want to use. And as I said, we are going to be looking at track number 1 for shot record 0454. So let's go ahead and find the same thing. Here I am in the exact same folder, but this is my C temp. I need to go up one right over here to 454. There's my track records, and it's going to show you all those tracks available to you. We said we're going to do shot number 1. Now the next part that I need to take care of is the elevation that I shot these. This is correct. 308 is the caliber of the bullet. 175 we already said. Now it doesn't know this automatically. This is from my default entries. The muzzle velocity we said is 2,165 feet per second. That's important to get these things correct. Once you've done that, you do not have to change the name of the output file. It will, and you can if you want to, but it will recommend an output file name based on the input. Notice, based on the input file name and its folder, and then it'll underscore output. So that's a pretty easy way to take care of it. We calculate the drag, and it's also going to calculate an average ballistic coefficient. Now that's quite high. Now we have to deal with this data reduction part. We don't have to, but it's going to make visualizing these data a whole lot better. We can use averaging. Okay, if you hover your mouse cursor over the top of this, it will explain what that's doing. Maximum signal to noise ratio, or the linearity. Linearity is recommended. So let's go ahead and check this. What linearity means is it's going to allow one record at a given velocity, and that next record has to be just a little bit slower than the previous record. Okay, so that's what that linearity is all about. It's sort of a logical check. Now we click Run the Data Reduction. Now sometimes after you run the data reduction, it will indicate that 0 records were found. If you see that, that means that, well, something wasn't right. And it actually is indicative of a poorly behaved, problematic bullet right off the bat. And your first indication is you're going to see some really crazy average ballistic coefficient, sometimes even negative numbers or very, very high, 1 point something. You start seeing that stuff, you know that that is not a good track. Lots of problems with it, and probably a very erratic bullet path. This one looks just fine, so now I'm going to click on Summarize that variability. Now let's go ahead and do another one. We are going to analyze shot number 4 from this same track. Notice as I open this up, it's showing me the ones that I just wrote, the files I just wrote. Don't try to analyze those. Those are not in the format to analyze. You got to analyze on shot 001, whatever, track files. So now we're going to do the 4, track number 4, bullet number 4, shot number 4. Notice, again, it is writing a good output file name for me. What was my muzzle velocity on that one? Do you remember? Well, it was 2,216 feet per second. A little bit faster, this one. Calculate its drag even higher. Okay. We'll see how that all plays out when we visualize this track. Run the data reduction. We see a nice 87 records. We can summarize on that. This is really purely optional, but let me show you now what we're dealing with. So I'm going to go into my track files right over here, back to Windows File Manager, and this is the initial output. We could look at the initial output, and actually we could, if we wanted to, we could graph Mach velocity by the coefficient of drag if you want to, but this is going to be a very messy file. Lots of records, but it's going to be messy because we haven't completed the data reduction analysis, and it's going to be harder for us to analyze it, visualize, interpret that data. I'm not going to use that one. Let's go back to that ctemp folder. This is the data reduction. Notice the DR linear tells you the method. You could actually run the data reduction all 3 different ways. You have 3 different files. So here's our data reduction file. Let's go ahead and launch that one. These are the 2 columns or fields of data we are going to use for data visualization. So I'm simply going to select these 2. Okay, so I'm going to click Insert, Charts, create a scatter plot, and I'm going to choose this one right here, Scatter with Straight Lines and Markers. Okay, so this is our graph. And since this has been reduced, the data has already been reduced, it should be really, really clean. It's not. This x-axis is our velocity expressed in Mach, and the y-axis is the drag coefficient. We should see a very smooth line, and really it should be just about flat. So I would not say that this is a very, very well-behaved bullet, simply because we have this, even after the data reduction process, but it is okay for it to have a slight upward trend from fastest to slowest, because as that bullet's velocity reduces, you're going to start getting more drag. So that makes sense. If I was analyzing, should I use this powder charge that was used for this particular bullet, I'd say, let's take another look. Hopefully we can find something a little bit better. It may also corroborate with an optimal charge weight or a harmonic node. So this is another way to analyze these data. Okay, so now let's go back and take a look at track number 4. There's track number 4. This is the data reduction using that same linearity method. Going to go ahead, double click that one. Again, it launches in Microsoft Excel. These are the 2 columns. Once again, I put these together. Initially, you had to do quite a bit of moving files around, lots of copying and pasting. This is so much easier to work with. Now again, insert, click on this little drop down on the side. Same thing. Okay, now this one looks actually even worse, doesn't it? We see a lot of variability right over here, some very odd behaviors right over here. And then actually it dropped, almost like a little smiley face it's creating right here. Not a well-behaved bullet also. And again, remember we had that fairly high ballistic coefficient average. So that didn't look good either. I'm going to drop this one down. Now let's take a look at, let's say this one right here. Shot number 9, which had a muzzle velocity of 2,126 feet per second. That's shot number 9. Going to go back to the software. Shot number 9. Let's take a look at this one. Only thing that we need to change on these initial, and these are important inputs, is the velocity 2,126. Again, the output file name's written for you. You can change it if you like, but you don't have to. Click on this one. And now, again, we're going to do this. 83 records written. It's just that fast. Boom, boom, boom. And you can go ahead and do this even much faster than I'm talking about it. This is the record then that was just created. Let's go ahead and graph this one. And now this looks really what we would expect. A very well behaved bullet, just a little bit of a blip right over here. I wouldn't be too concerned about that. But the fact is that we are almost perfectly straight, and that's exactly how that part of the curve of the drag coefficient for a bullet in this velocity range, it should look just like this. It should be, as I said, almost perfectly flat, and if anything, just a little bit of an increase, just a slight increase as you slow down. This is really nice. This is really, really nice. So we like to see this. This is what we call a well-behaved bullet. It looks really, really good and when we're analyzing the intermediate ballistics here. One more thing I'd like to show you that you might be interested in looking at is the summaries. So here's our summary. This is the summary based on, again, the data reduction using a linearity approach, and we get the mean coefficient of drag out to a maximum of 25 yards. If you calculate the mean coefficient of drag or drag coefficient, the variance and all this good stuff like we're doing here, if you do that over too long a period of time, or you can think of it as distance, if it's too long, you're going to have tremendous amounts of variability just because that bullet is slowing down. So what I've noticed is that at about 15 yards, that's usually where we start getting some good records of data. And so we're running it for 10 yards out to 25 yards. That's the mean drag coefficient. And here's the variance. Notice that is a really, really small number. Let's take a look at the variance of the drag coefficient for another bullet, a less well-behaved bullet. Now for this example, I'm going to navigate over to one of the tracks that I analyzed when shooting the 300 PRC with that initial load workup for the Berger 225 grain bullet. And specifically, the one I'm interested in is shot number 1 right here. Notice this drag variability value right here. It's just literally gigantic. Is it really that bad for that bullet? No, but the data that we gathered with it, I'm assuming, and I'm interpreting this to be a very poorly behaved, erratic bullet as the first, 10 meters of its flight path, and it did not behave well. Well, if you don't start the flight path very well, you don't start it correctly, you can't expect too much. So this one looks really, really bad, and another indicator that this is not going to be, or probably not going to be, a very good bullet. or load to choose for this bullet. Thanks for sticking around for just a quick recap. On a few occasions now, I've been able to use those Doppler radar tracks to help me develop a very good load. And what I'm looking for in those tracks is a very smooth and flat drag curve. Doing it by hand, like I showed in a previous video, is doable, but using the software I developed makes it really, really easy and fast. Now, this process has worked for my 300 PRC and loading the 225 grain Burger bullet, and it has also worked for the 175 grain Sierra Match King for my son's HK MR762. Is it just luck or coincidence? Well, I'm not sure. It has worked out really, really well, but I suppose it's possible that it's just a coincidence. I'm going to stick to it though. I'm going to continue using this method as well as optimal charge weight and harmonic nodes to develop my loads in the future. One of them that I'm going to be working on is the 167 grain Lapua Skinner for my 308 Winchester. Now, should this method replace OCW, optimal charge weight, or harmonic mean? No, as I already alluded to, this is just another tool in our toolbox to help us develop precision rifle loads. Now, if you'd like to use this software, it's free. I'm making it freely available. Just use the link that's in the description. And I've also included a little README or how-to file in that zip file that you're going to download. Pretty darn easy to download it, access it, and then, as you could see, make use of it. And I'm interested in your ideas about this entire method, or if you do download that software and use it, I'm interested to see what you think about it. Please post those in the comment section below, and as always, thank you for watching.